Welcome to Practical Engineering. My name is Robert, and I've thought a lot about making a YouTube channel for about a year or two now. And what I really wanted to do is something different that I haven't seen out there. I've seen a lot of people, makers and whatnot, make channels where they build things, and I've seen a lot of people in the manufacturing realm have great channels where they show off, their manufacturing skills and different techniques to accomplishing certain projects. But what I haven't seen is a channel that really goes through the entire design process of projects from an engineering standpoint. And I would like to have a channel where I show how to do this. I will focus some on manufacturing, of course, and some on building things, but for the most part, the channel is going to be based around the design and construction and modeling of different projects and how to accomplish this, and from what I see, the best engineering practices and standards and ways to build things. I solicited the solicited the advice of an internet forum called Practical Machinist on whether people thought this would be a good thing or something that they would actually like to watch or enjoy watching. And I got some positive feedback, and I had an idea of what I wanted the first project to be, and that was a project on pressure vessels. I haven't seen a real great video series on how to build and design pressure vessels. They're somewhat complicated and quite frankly can be pretty dangerous if they're not, constructed correctly. And I think that'd be a really good topic in the future, but someone suggested another topic that I think wouldn't necessarily be more simple, but can cover a lot of basic engineering principles and can help kind of get an introduction to the channel, and that would be to build a hydraulic press. So let's jump right into this. Building a hydraulic press is not going to be too complicated. There's not a lot of parts to a hydraulic press. You have the cylinder itself, you have a structural piece at the top, you have the structural pieces linking the top to the bottom, and you have some other system components such as a pump and a control system. Now, the parameters that define the press itself are the stroke, the daylight, the length in this direction, and as well as the width of the press. So those are important to define before you start the project. Usually the best way to define those is to just figure out what do you want to stick inside this thing to press on. It could be as simple as trying to remove bushings from parts to something as complicated as pressing a mold with metal or plastic or something like that inside of it. So moving on, let's talk a little bit about the system overview of the press. So we have the press itself that we talked about a little bit earlier, and we have the hydraulic pump that powers or gives the power to the press. Not all presses are going to be hydraulically operated. Some can be mechanical or electrically operated. And we have some sort of control system that controls the pump as well as the motion of the press. And that'll consist of hydraulic controls as well as electrical controls. The heart of the press is going to be a cylinder. In this case, we're going to use a double acting cylinder, or a cylinder that'll go both up and down or in and out. The way this works is fluid comes into the top of the cylinder to make it extend out and forces this piston down, and when you want to make it go the other way, fluid comes in the opposite end and fluid goes out the top side, and it forces the rod back into the cylinder. So in order to make that cylinder function how we want it to, we need to devise some controls, and the controls that I want for this press are a speed control for the up, a speed control for the down, a rapid up, a rapid down, some sort of way of controlling the force in any direction, as well as possibly some folks would maybe want a limit control and a displacement control. Now, I'm going to forewarn everyone, I am not going to actually build these last two parts. They can be pretty complicated. The limit control is not too bad, but the displacement control requires us to build the press in a manner that's just way too complicated or expensive for what we're trying to do. So this project itself, I want to divide up into a few parts. the first phase is going to be a design phase. The second phase is going to be a build phase, and the last phase is going to be a testing phase. So during the design phase, what we'll begin with is the actual design of the press physical components, the two structural components. So we'll design and come up with equations to specify this top portion here, each of these little side pieces here, this bottom portion here. We'll design the actual cylinder itself, and we'll design all the bolting connections to make sure everything goes together and doesn't come apart when we apply maximum force or maximum load or maximum displacement or maximum speed. The second thing that we'll design is the cylinder assembly and the hydraulics. This is somewhat separate from the controls. The hydraulic controls are a little bit different than the electrical controls, but we'll somewhat try to divide these into three separate portions. I think we can accomplish each one of these possibly in a 30 to an hour video, but it could be longer. I might have to break them up more than that. Now moving on to back to the build phase, we'll try to go through some of the manufacturing and procurement of different parts. Unfortunately, I'm not sure that I'm going to actually build a new press for this project. We might though. I'm still on the fence on that. They can be pretty expensive, especially the manufactured parts, and I've already got several functioning presses. So what we could do is we might go over the necessary steps to do that and talk about them, and then utilize the components I already have and go through the assembly, especially on the hydraulics. I actually have specified out a new hydraulic system for some of the presses that I have, so that could be real easy to show the assembly of the hydraulics. And I think honestly the manufacturing of the press components themselves is such a simple process that there's been so many other videos that have gone over that sort of manufacturing that it's really not going to add anything to what's already out there. The assembly, though, there are some interesting things that we would have to do or we would want to do when assembling this press that I think is worthy of going through. So we'll definitely take one of the presses, or I'll take one of the presses apart that I have now. I have a few that need to be moved anyway, and we'll go through the assembly process of that. Now the testing and validation. This part, I'm not sure how much I want to get into it, but I think what I do want to do is we'll do some strain gauge testing on a few parts, and we'll also do some load testing just to make sure that the press says that it produces the load that it says it does. We're going to use a few different tools to accomplish building and designing of the press. One's just going to be obviously what I've been using so far, which is pen and paper. I really like pen and paper. I'm not an old guy, I'm pretty young, but at the same time, I feel like it's a lot faster process than trying to build models in CAD for everything. The second piece of, or the second tool that we'll use is going to be an Excel style spreadsheet. In this case, we're going to use Google Docs. It's free. Everyone can use it. I don't really have a problem with it. It's not my favorite thing to use, but it works pretty well. The third thing we're going to do is use Google extensively to find information and to track down where to get things. I don't really want to show people how to Google stuff, but I definitely will go through and show you where I got the information from. There's a few engineering websites out there that are really good and give you a lot of information. The next piece of equipment that I think we're going to use in order to accomplish all of our CAD and modeling is this program called Onshape. Onshape is a free CAD software. It's pretty good. It's almost exactly like SolidWorks as far as its usefulness and how it works. It is limited in capabilities. I will forewarn everyone, I do not use Onshape in my professional life. It does not have certain drawing features that we have to have as a manufacturing company. And for that reason, I flat out, I can't use it. But it is a really, really good program. My small amounts of use with Onshape have been positive, and I like some of the features it has a little more than SolidWorks. So this is the program that we're going to use and that I'm going to demonstrate, how to use. I think it'll be pretty good for us. And again, it is free and readily available to anyone who wants to use it. Now, I want to talk a little bit about specific programs, such as things like, for example, finite element analysis. On a project like this, FEA is really not necessary. This is simple stuff. You should be able to to build this entire press based off of equations from the machinist handbook, there's there's really um, there's really no reason to use something like FEA. That's way beyond the scope of what we're doing. I also don't think it's a good idea to try to rely on those things when you're doing simple projects. And if you have to do something that is complicated enough to warrant the use of FEA, then you should definitely be starting with simple equations and trying to model things simply before you get to the complicated states. So the next thing I want to do is come up with, basically we need to make some decisions that have to be made in order to move on with the project. And one of those sets of decisions is going to be to flesh out these initial parameters. I have some stuff written here. This is not what we're going to end up with, but I am going to do some measuring of some parts that we are going to make, and I'm going to come up with these parameters such as the daylight stroke, tonnage, the action, the press mechanism, the frame construction, the width, the depth, the budget, the electricity availability, the time frame, the controls, and the footprint that we have to stay in for our press. And one of the key things in order to define all this stuff is really this press is going to need to be built around a hydraulic cylinder. Now there's several options for hydraulic cylinders. The first option is to buy something used. Surplus Center is a great resource for hydraulics, especially on the used side. Um, they have a great website. You can go in here and you can pick basically anything that you need. Uh, so in order to choose a cylinder, we really need to come up with the capacity of this press. So I'm going to choose an arbitrary 40 to 60 ton capacity. And what this capacity is going to do is this is going to allow us to select a cylinder based on this. So we know we want a double acting cylinder. We want it to be 40 to 60 tons. System pressure for hydraulics commonly is 3,000 psi. That's a pretty common standard amount of pressure that you're going to be able to find. So with these three components, we're going to definitely be able to narrow down our cylinder choice. I want to start by saying in these videos that I wasn't born with any of this knowledge, and I in no means, if you feel confused or you feel like I'm not explaining something properly, don't be afraid to ask. Again, I was taught all of this stuff by someone else, and I had to figure all this stuff out, either by the way of teaching or on my own. And it didn't always come real quickly. So I think that if something's not clear, please ask me in the comments, and I will do my best to create other videos to explain stuff and to make it as clear as possible. After recording some video, I think I might have jumped into some things a little bit too quickly, and I wanted to come back and just discuss a little bit about the principles of operations of hydraulic systems and why we use them and why they work. The principle of hydraulics revolves around force over area. So pressure equals force over area. Okay. This is a governing equation for hydraulics, and it's very simple. If you apply a given force to an area, you get a pressure. If you apply a given force to an area, if you apply a given pressure to an area, you generate a force. So these items are all related to one another. We can rewrite the equation again with force over pressure equals area. And this is kind of the governing system that you use to figure out things in hydraulics. Okay, and they work. The force over area works for hydraulic motors. It works for hydraulic pistons. It works for all sorts of hydraulic devices. And the reason this is important is because what you can do is you can have something that is very small, a small amount of force. Like say you have a weight that weighs 1 pound. Now, if you put that weight over an area of, say, 1 inch squared, you get 1 psi. Now, if you were to put that same weight over an area of, say, 1/1000th of an inch squared, now you have 1000 psi. However, if you think about it, that there's got to be a trade-off between these two, right? And the trade-off there is that for every inch that you displace this weight at the given area, you're going to generate a certain volume change of fluid. So what we can think about is say that we're at the 1 psi 1 psi level here. So for every inch that this weight was to sit on top of this cylinder, it's an infinitely long cylinder. You know, every time you move down an inch, you get 1 inch cubed of fluid that moves out. Now the same thing for the really tiny 1/1000th of an inch squared area cylinder is that, that every time it moves an inch, you only get 1/1000th of an inch cubed in volume displacement. So you can think about this, you've got to push a lot longer, you've got to push a lot further, 1,000 times further for this one to get the same amount of volume as this one. So that's not, that's not really that important when you're trying to generate a static force, but when you're trying to move something large that requires a lot of volume displacement, then the amount of work that you have to do is significantly increased. So the amount of work to get this 1000 psi is nearly is 1,000 times more than the work to get the 1 psi with the same force. And this in a hydraulic pump is what's related to getting your horsepower and the energy that it actually takes to power the system. So looking at the other direction of this is say that we have this 1 psi weight, this 1 inch cylinder with a 1 pound weight, and we generate 1 psi. Well, we can theoretically move very immense loads if and only if our cylinder has enough area. So for a 1 psi system, say we needed to move 1,000,000 pounds. Well, in that case, we would need a 1,000,000 square inch cylinder in order to move that 1,000,000 pounds with just slightly more than 1 pounds. But again, that trade-off comes into play here. So say you have that 1,000,000 pounds on top of the 1,000,000 square inch cylinder. Every time you put a cubic inch of fluid into that cylinder, it's only going to move the cylinder up or down by a 1/1,000,000th of an inch. So there lies the problem. You have this balance between, hey, small amount of force over a small amount of area doesn't give you very much distance traveled. I hope this somewhat clarifies, how the force, the pressure, and the area interact, and kind of why we use hydraulics. Because again, you can use small amounts of force to generate very large amounts of force. However, there's a trade-off in the amount of work that you have to do in order to generate the motion. So the way we will be able to make that cylinder choice is pretty easily. So we know we have a maximum pressure of 3,000 psi, and we know we want 40 to 60 tons. So 40, we can start at the low end. So 40 tons times 2,000 pounds, that's going to give us 80,000 pounds. And on the high end, that's going to be 120,000 pounds. Okay, and in order to convert this to cylinder diameter, we know that we have a 3000 psi maximum system pressure. So if we take 80,000 and divide it by 3000, that will give us our particular pressures that we need. And forgive me for not being able to do this in my head, but I'm going to use a calculator here. So that's saying that we need a 27-inch squared area. And on the other one, we are going to need 40 inches squared. So once we have the area that we need to then find the diameter that we need. So that's pretty easy. You know, the diameter, the area of a circle equals pi r squared. Okay. So if we solve backwards for r, which we can get d out of, because r 2r equals d, then we can come up with the radius or the diameter that we need. So we know we're going to have two different ones. 27 and 40 is going to be our a variable. So the first thing we'll do is we'll do a over pi is going to equal r squared. And then if we take the square root of a over pi, that's going to equal r. Now, if we substitute in, if we try to substitute in for d, we can do r equals d over 2. And if we plug this into this equation, we get the square root of a over pi equals d over 2. Multiply both sides by 2. D equals 2 times the square root of a over pi. So we then solve this equation and we're going to get our diameter. So that's 8.6 under the radical. And we got 12.7 under the radical. So that one equals 2.9. So if we substitute these two back into this this r equation, or we multiply them by 2, basically, we're getting that we need a more or less a 6-inch diameter, and we need a 7-inch. So we need a cylinder that's 6 to 7 inches. And if any of this is confusing or you don't follow, I can make a separate video that shows this over again and try to simplify it out or make any steps that are lost more clear. So now that we've narrowed down our search to the diameter that we need, I've gone through and kind of looked around at what they have there just so we don't have to spend so much time on their website. But basically what I've done is I've gone to hydraulics, I've gone to double acting cylinders, and I'm trying to narrow down our range of things that we want. I went to 7-inch and larger because I feel like there's a cylinder here that'll work. And I've come across the cylinder I think that is good for this project, and it is this guy here, this 7-inch by 69 by 5 inches. So now that we have this cylinder selected, we're given quite a bit of information. I say quite a bit, we're given enough information that we can successfully model this cylinder in our CAD program and use that to start our modeling and to begin the design derivations or iterations in order to create the press. So it's got some good information here. It's got the bore, the stroke, the pressure, the diameter of the rod, the end mounts. It also has the ports on the cylinder, the retracted length, the flange to base length, the shipping weight, which is important for shipping, the front mount, the flange size, and the bolt spacing, so as well as the hole size. So we're going to use all of this information in order to model the cylinder in Onshape. So now it's time to put this cylinder in Onshape. First we will start by giving it a name. We will select the front plane here, and we will put a sketch there. Okay. And you're gonna kind of have to watch me struggle through this just a little bit because I'm not exactly an Onshape expert, and a little bit of it is quite a bit different than SolidWorks, but most of it's pretty much the exact same. So we're gonna make this the inside diameter of the cylinder. It's not really necessary to to make this as it is, but just in this case, I'm going to go ahead and do that. Now, unfortunately, this does not give us the dimension of the actual outside of the cylinder. I'm going to make an assumption, and I'm going to say that it's not going to be much bigger than 8 inches or maybe 8.5 inches based on these pictures. And sometimes that's just something you have to do whenever you're presented with surplus equipment, or you're trying to model something that you don't know exactly. You just gotta you gotta just make a decision and put it in there and live with it, good or bad sometimes. So now we're going to extrude the cylinder out. We're gonna go ahead and make it the length specified here, which is 76 3/4. Not 100% sure that that is the entire length of the base to the back end of the cylinder, but I believe that's what they're saying there. It'd be helpful if they would provide a drawing, but they don't. So it's kind of the best you can hope for there. Some of the stuff on their website's a little bit more more detailed than others. We're going to close the end of this cylinder with another extrusion. That's one nice thing about Onshape is that you don't have to make a new sketch all the time for the extrusion. I feel like you have to do that more so in SolidWorks. It's a little bit more intuitive sometimes. So now we're gonna go ahead and create the flange over to here. So we'll start out by creating a square, 12 inches by 12 inches according to the drawing that we got from them. There we go. If you guys are picking up any background noise, I do apologize for that. I don't have the best of mic set up since this is something new that I'm doing. I'm trying to just kind of trying to work with what I got, which is a pretty standard headset. But if this is if anyone if this actually is well received, I might upgrade some of my equipment. One thing that's a little strange about Onshape is the way that you select constraints in a sketch seems to be a little bit different than SolidWorks. For whatever reason, it seems like they're missing a collinear constraint, but maybe that's just just kind of what I'm doing here right now, and it's just a little bit odd for the program or something. I'm not entirely sure. specify this dimension from here to here, which is going to be the difference between 12 minus 7.75 divided by 2. This would be 2.125. And I'll specify the dimensions from here, here to here. Then we'll just make our hole size. Done with that, extrude that portion. And it needs to be the opposite way and 1¼ inches. And that'll do it for the body of this cylinder. I'm going to create another part for the actual rod. That way we can manipulate it inside. So we'll pick up there. So picking up at the hydraulic rod. Design this simply enough. Again, start at the front plane, create a sketch there, circle. I'm using keyboard commands for some of this stuff. It's just what I'm used to. Luckily, the keyboard commands in Onshape are pretty seem pretty intuitive. This is all just arbitrary lengths. They aren't really all that important. Some sort of error here. Let's see what they're saying. They're saying that so it's not saying that we're not selecting something on this extrude. I'm a little bit confused there. Let's try this again. Extrude solid from sketch 1. Extrude that, say 4 inches. Okay, there we go. And we'll make this part the actual same dimension as the rod. And we're going to make it slightly longer than the stroke. I'm going to give it 2 more inches than the actual stroke of the rod, just in case, you know, we need to put some stuff inside to manipulate it. But I think that should be pretty well. So make that 71 inches. Check. And we have our cylinder rod. One note is that in Onshape, I'm not exactly sure why it does this, but every time you make a drawing, you have to go back into the drawing, it seems, and in order to put it in an assembly, you have to save a version. So in this case, it's wanting me to version 2, but I've already previously created versions of each of these so that we could place them in the assembly. Parts inserted here, and I'm going to mate them. I've off camera, I've done a little bit of research and figured out what I was doing wrong and what I need to do. So it seems like this is the slide mate is the proper mate to use here. And everything in Onshape is a little bit clunky. Honestly, it's if SolidWorks is clunky, this is even worse. Which SolidWorks is pretty clunky. But a lot of times it's struggling with doing things in a semi quick way, even though it's supposed to be cloud-based and not use any resources on your computer, which I can fully see that it's not. It's just every time you go to insert parts or mate something up, there's a little bit of lag there, and sometimes you're not exactly sure if it's you or the computer or you're doing something wrong. So that's definitely something that they need to fix up a little bit. So what I can do here is fix this component in space. And then we have our cylinder, which needs some work, but anyway, as you can see, you can slide it around inside and out. So that's going to be somewhat the end of the first video. I'm going to gather up a lot of the parameters today and get ready to make another one. I think in the next video, what we'll do is we'll model the rest of the components for the major components for the press, and after that point, after modeling the components, we will then perform calculations on them to get them to a point where they're actually ready to be manufactured. Mostly it'll be strength calculations. There's not too much other stuff we need to do for them, but that's what's the next step.